see an example. You can see at the top of the board, I've written in tiny letters a reminder of what Green's theorem is saying. Green's theorem is saying that I can take a line integral along the closed boundary, of D. My vector line integral is going to be exactly equal to the double integral over the area of D of the curl of my function f, where my curl is given by this expression. So let's see an example where, in this case, my vector field f is given by x to the fourth comma xy. And C, our is going to be a triangular path. And this triangular path goes from 0, 0 to 1, 0 to 0, 1, back to 0, 0. So I'm going to go ahead and sketch what that triangular path looks like. Notice that we're starting down here at 0, 0, and then we're going to 1, 0, and then we're going up to 0, 1, and then back to 0, 0. So really, our triangular path is a path that looks something like this. And we're going to compute this two different ways. We're going to compute it using our line integral way, and then we're going to compute it using our fancy double integral over the area way. We'll just start with this one for no particular reason. So let's see, what is this asking? Remember that this is just the notation that says that we're going to be taking the line integral over this path for this function. So there are a couple of things that we're going to need to do. We haven't talked about piecewise paths yet, that we can think about this. This is a closed boundary. Notice that we've oriented it so that it goes counterclockwise. That was one of the requirements of Green's theorem. And we're going to evaluate it piece by piece by piece, meaning that I'm going to find the path integral over this chunk, and then this chunk, and then this chunk. So the first thing that I'm going to do is I'm going to represent three different paths. The first path has to go from 0, 0 to 1, 0. So C1 of t is going to be a path where my x coordinates go from 0 to 1. So I'm going to set that equal to t, and my y coordinates stay constantly at 0. So in this case, t is going from 0 to 1. And that traces out this pretty basic linear path. That's what C1 is along the bottom. C2 is going to be a little trickier. That my y coordinates are increasing from 0 to 1 at a continuous rate. So I'm going to set my y coordinates equal to t. But my x coordinates are going backwards. They're starting at 1 and they're going to 0. So by starting at 1 and going to 0, if I start with t equals 0, my x value is at 1. And when t equals 1, my x value equals 0. So I use 1 minus t in the x component and t in the y component. Again, t is going from 0 to 1. And then finally, my C3 of t, here my x coordinates are constantly equal to 0, and my y coordinates go from 1 down to 0. So I can use 1 minus t again, which will make my t's go from 1 when I plug in 0, and 0 when I plug in 1. So really that was just setting up the path, and that's a little bit of work, but I think it's important for us to review or to work on how to set up paths for straight lines, and these are ways to set up paths for straight lines. So how can I interpret this and turn this into a line integral? Recall, what is our line integral? We're going to have to do it piece by piece. So let's look at the first path, the C1 path. And I'm going to look at what is f of C1 of t. In this case, I'm going to plug in C1 of t, where my t values are x's and my y's are 0. So this just becomes t to the fourth, comma 0, because y is 0. And my c prime of 1, c1 prime of t, is the derivative of this path, which is just the 1, 0 path. So that means that my first line integral piece, the piece that goes from 0, 0 to 1, 0, is going to be the integral as t goes from 0 to 1 of f of c of t, which is t to the fourth, 0, dotted with c prime of t, which is 1, 0, dt, which ends up being the integral from t equals 0 to 1 of t to the fourth, dt. And I can integrate this almost in my head. That becomes t to the 5th times 1/5. And when I take that and evaluate it at 1, I get 1/5. And when I evaluate it at 0, I get 0. So this is our first path integral. And I'll save it up here. Let's do the same thing for C2. C2 now, f of C2 of t is going to be evaluated where my x values are 1 minus t to the 4th, and my xy term is going to be 1 minus t times t. Notice that this is a little more complicated than the last one. We're going to need to do a little more work. I'll keep this 1/5 up. This 1/5 was our first path, our C1 path. We're also going to need to find out what is C2 prime. What's the derivative here? I get the derivative of 1 minus t is -1, and the derivative of t is 1. So when I look at the dot product, maybe I'll simplify this a little bit. I don't think I want to write it out. I think I want to keep this first term the way that it is. I'm going to keep it as 1 minus t all raised to the 4th power. But this second term I'm going to turn into t minus t squared. And what is our integral? This is written in terms of p's and q's. I don't really care that it's written in terms of p's and q's because I know what a line integral is. It's going to be the integral as t, in this case, goes from 0 to 1, of this dotted with this. So my first component times -1 becomes negative of 1 minus t to the 4th. Oh gosh. Well, it's okay. And then plus 1 times my second component, which is t minus t squared dt. I'm going to integrate this. Integrating this, I raise this to the 5th power. I'm doing a u substitution in my head, actually, and I get 1/5, 1 minus t to the 5th. I needed my u substitution, gave me the negative, which cancels with this negative, plus 1/2 t squared, minus 1/3 t to the 3rd, evaluated from t equals 0 to 1. When I plug in 1, this term becomes 0, and I end up with 1/2 minus 1/3, minus when I plug in 0, I get this becoming a 1, so I get minus 1/5, and this is my value for C2. I'm not going to simplify it because I see that it might cancel with some of these other pieces later on. Finally, let's compute one last of these line integrals. This last line integral is going to be for C3. So f of C3, I'm plugging in 0 for x, and thankfully, whew, that just gives us 0, 0. The derivative here, I actually don't even need to compute it, because I know that when I take the dot product of 0, 0, which is f of c of t dotted with c prime of t, I'm just going to get out 0. The integral of 0 is 0. So this third, the amount of work that's done along this final part of the path, is exactly equal to 0. And that's because, you can think of it, all of the vectors along here are exactly 0 vectors. There are 0 vectors all along here because the x components are all zeros. And so it makes sense geometrically why the vector line integral along this final line is equal to 0. So, what's our final answer then? So our final answer, our vector line integral along the closed path that was the boundary of D, written p dx plus q dy, is going to be the line integral along each of these boundaries, which we found were 1/5, plus for our C2, it's going to be 1/3 minus, no, 1/2 minus 1/3 minus 1/5, plus 0 for our third boundary. And we see the 1/5 cancels with this 1/5, and we end up with 1/2 minus 1/3, which I think is a sixth, which is 3/6 minus 2/6. Yep, it's a sixth. Hooray! Wasn't that fun? No, that was pretty tedious. Doing this line integral actually wasn't that easy. So let's use Green's theorem. Same problem, only this time instead of computing the line integral, we're going to compute an area where the function is given by this. So we can't just use, maybe this is, say, caution. It's not the double integral of f. That's wrong. And you'll be tempted to do that, because f is a vector. You can't even plug a vector and take some. Anyway, so we aren't going to do that. First, we have to compute the scalar curl. So we can compute our curl, which is the partial derivative with respect to of q with respect to x minus the partial of p with respect to y. And recall, in this construction, q is always the second term. Maybe I'll write it in the right order so it'll be more helpful. That p is always equal to the first component function, which in this case is equal to x to the fourth. And q is always equal to the second component function, which in this case is equal to xy. So I'm computing what is the partial derivative of q, which is xy, with respect to x, minus the partial derivative of p, which in this case is x to the fourth, with respect to y. And here we see, what is the partial derivative of xy with respect to x? That's just going to be equal to y. What's the partial derivative of x to the fourth with respect to y? That's just 0. So in this case, our whole curl term is equal to y. Y minus 0 is just y. So now we're going to compute our double integral of d of the curl, which in this case is y. And how do we set up a double integral? Well, we have this region, and we're thinking of this triangular region as our region. I'm going to break it up as a type 1 region. What are the bounds on this type 1 region? I know that my y values are going from 0 up until this line. This line is given by y equals 1 minus x. Its intercept is up here at 1, and it has a slope of -1, so that's the negative x. So that means my y values are going from 0 to 1 minus x. My x values are going from 0 to 1 of y dy dx. And this is old school. I mean, we can do this. There's nothing new or crazy about this. I'm going to take my derivative with respect to y, my integral with respect to y first. So treating y as the variable, there's no x here. I end up with 1/2 y squared evaluated from y equals 0 to 1 minus x. I plug in those bounds and I get 1/2 of 1 minus x squared minus 1/2 of 0 squared. My lower bound is 0. That just becomes 0. And this chunk, whoops, I'm missing a little dx out there, is the integral as x goes from 0 to 1 dx. So I'm going to integrate this with respect to x. And what do I get? I raise this to the third power, so I get 1/2 times 1/3. I raise it to the third power, so I have to multiply by 1/3, minus, or times 1 minus x to the third. But in order to do that, I have the fact that my u substitution must have had a negative, so I need to add a negative somewhere in here. Whoops. So I've taken this integral, and now I need to evaluate it from x equals 0 to 1. When I plug 1 into here, notice I get 0 out, because 1 minus 1 is 0. It all becomes 0. So I get 0 minus, what happens when I plug in 0? I get negative 1/6, which is equal to 1/6. Hurrah! In this particular example, we got it to line up. That when I took my line integral along this boundary, it's exactly equal to the double integral over the scalar curl of our function, which in this case was equal to 1/6. I think I'll post some other optional examples. Really, all of this computation is something that should be sort of familiar. As soon as I get this set up as a double integral, that's just review. Something to keep in mind is, what am I integrating over? I'm integrating over my region D. And if my region D were a circle, I might want to convert it into cylindrical or spherical coordinates. Or actually, it's always going to be polar coordinates because we're always just stuck in R2. That's it. I'll stop rambling.